Welcome everyone at our NetPlace seminar. So today our host is Barry O'Reilly, that we talk about an introduction to residuality theory. So go on, Barry. Thank you for being here. And
okay, thank you. Let's get started. So this is going to be a brief and very quick introduction to residuality theory, which is a theory that I've created over the last couple of years during my PhD. My PhD subject is complexity science and software engineering. What I'm doing is trying to figure out more rigorous ways to allow software engineers to make and document their design decisions so that it becomes more akin to other engineering disciplines rather than the kind of haphazard structures that exist today for making decisions about component structures. I'm a part-time PhD student. I'm nearing the end of my PhD, but I've been working in the software industry for about over 20 years, previously being a chief architect at Microsoft and a global lead for architecture at Microsoft in a previous life. And what we're going to talk about now is written about in this paper, which was released about 3 or 4 weeks ago on Procedia Computer Science. I'm going to talk about the relationship between residuality theory and something called residues, random simulation, and attractor networks. So the basic problem that we have in the software industry, which isn't really described particularly well, is that we build these structures of software components that communicate with each other, that are connected to each other, and we can view them as systems. And these systems are not generally particularly complex. They're very ordered, very structured, and we're in complete control of the structure. And we, as the programmers, as the designers of these things, are in control. And that makes software, essentially from an engineering perspective, something that's very, very simple. Until we take these little pieces of innocent, complicated software and we force them to live in a complex enterprise or business environment. And in that environment, we have all kinds of things swirling around, things like financial concerns, economic concerns, social structures, organizational structures, market structures, and competition, and things that Western science doesn't really have a handle on. This bubble that we force our applications to live in is unpredictable and deeply, deeply complex. And what happens is that whenever we build these little software structures and put them into this environment, this little X pops up that we didn't design our system for, that we didn't understand that this was going to happen or that this was even possible in this environment. And there are lots and lots of these little X's, and they pop up. And as soon as they pop up, they put pressure on the software and they make the structure that we have come up with irrelevant. And the structure is now no longer sufficient to meet the needs of the people who have paid for or are using the software, which means we've got to go in and change that structure. And as time goes on, changing the structure becomes expensive and incredibly difficult for us as software engineers. And the way that we've coped with this problem over the years is to pretend that this large bubble of complexity that surrounds our applications is actually really small. And we use a number of techniques that are essentially social techniques to make the bubble appear smaller. One of them is called requirements engineering, where we ask people who are involved in the effort, what do you want, when they can't possibly describe all of these X's that are going to pop up. And we use something called risk management, which is a way of assigning probability to things that we don't understand. So it's kind of theater, but it allows us to reduce the bubble to this inner circle, which has significantly fewer X's that can pop up. And that allows us to act, it allows us to start building things, and it allows us to give the impression that we are actually in control. As soon as we do that, though, this red X, another X, pops up in reality and does exactly the same thing. It destroys our software system. And 20 years ago, we realized that we need a different way of thinking about software if we're going to be successful. And that gave rise to something you might have heard of called Agile, where we build software as a reaction to what's happening in the environment, as opposed to trying to plan and predict everything that's going to happen in the environment. And this Agile has shown us that that's not enough to just react when things change, because even when this X pops up, we've already made structural decisions in our software. And those structural decisions mean that they can restrict our ability to act in the future. And that's the major problem with software architecture today. We don't have a rigorous way of doing this. We don't have an explanation or a theory for doing this, and we don't really have a great theoretical base in software engineering anyway. And so the challenge is, can we find a different way to do this? And one of the things that's really interesting is that even though this problem, which sounds impossible to solve, exists, there are a number of architects out there, senior architects across the world, who successfully deliver software over and over and over again, too many times for it to be random. So some of us in the industry know how to do this. And so this entire project has been about how do we codify that. There was a book written in 1981 by a guy called Donald Shahn that describes this kind of process, how professionals end up, after a number of years of practice, being able to navigate seemingly impossible to understand or document complex environments. And that's where we are now as an industry. It's a reflective form of practice. The problem we have as an industry is that we need a lot more architects all of a sudden, and we can't produce them fast enough. So it takes about 15 years to go from someone with a graduate degree in computer science to be an effective software architect. And so one of the things I realized when I started digging into this and trying to figure out how do we create architects faster is that the people who are able to do this have a much better handle on uncertainty. They're much more comfortable working with businesses and software projects where they don't know everything, and it's okay not to know everything. So I started digging around the area of complexity science. And what I realized was happening was that we were solving problems in a way that the complexity community had already been doing things for a very long time. And one of the ways that we solve complex problems in general is to do random simulation. And most of you, I think, will probably be familiar with the idea of a Monte Carlo simulation, where we can take this circle in a square with a side of length x and estimate by taking sample points inside the shape and saying, is it in the circle or not? And if we take 2 points and one of them is in the circle, one of them isn't, then we can say that the area of the circle is roughly x squared over 2. And that seems really simplistic, but if we do that for a lot of points, then you can get a fairly accurate estimate of the area of the circle and a fairly accurate estimate of pi. And I'm sure that must be something that's familiar for this group. And this is one way to deal with uncertainty. When we don't have control over everything, we can't measure everything, it's not possible, then random sampling, random simulation is a good way to get a handle on what is this environment. And this, if we look at those techniques that we've been using within software engineering to gather requirements or predict risk or impact of a risk, then what we're actually doing all the time is random simulation of the environment of this huge bubble that we're going to place our application into. And that's something that is not particularly shocking, I'm sure, for this group, but for software engineers, that's a big statement to say that actually all of these structured theoretical models that you've been using for 40 years are no better than throwing a dart at a dartboard. It is kind of provocative. Another thing that I've taken from the complexity sciences that's really interesting to the work we do is the concept of Kauffman networks. And a Kauffman network is a random Boolean network, and it's best thought of as a bunch of light bulbs. And each of these light bulbs have two states, on or off. And if we just have a number of light bulbs like we have here, unconnected to each other, and each of these light bulbs has a little function. So when they receive an electrical signal, the function decides randomly, am I on or am I off? A system like this has 2 to the n states. And Kauffman did some experimentation with this and found some really interesting results, that when he started to connect these nodes to each other so that they sent signals to each other, and those signals became part of the random, became an input to the random function that made them decide whether or not to be on or off. And he ran computer simulations on this kind of network. He found that the number of states that the system arrived in was consistently much smaller than 2 to the n. And what he found was that it was roughly root n. And he called these root n states attractors. And so these systems tended to go through a number of states before they arrived and settled into a state, which he called an attractor. And that's really, and that's something that's really interesting. And it will be important as we go through this. And so one of the things he then started to do was to, and he called his model the NK model, was to analyze these networks from a number of different properties. One of the important properties was the number of nodes. How many nodes are there in a network? In this case, we have 12. K, which is the degree of the network, what's the average number of connections for every node? And P, which is important in the software context, which is about bias. And P was a measure of how likely or unlikely one of the nodes was to repetitively engage in the same behavior. And so if a node did the same thing 90% of the time, then you would say it had a high bias. But if it had 3 options and it did 3 different things 33% of the time, then it had a very low bias. And he discovered a number of things. He discovered that the higher n is, the more disorder you would see in the network, the more attractors there would be, and the higher. And he discovered that especially that K determined how much order and disorder, how much stability there was in the system. So if K was 2, then he's seen that the system was stable, and that when you stress the system, when you change something, it would always return to the same attractors all the time. When you raise K up, then the system starts to become unstable. It starts to have a much greater range of attractors and starts to be unmanageable. And Kauffman then came up with, not Kauffman, a few years later, we came up with the idea of criticality, or the edge of chaos, where a system settles on a value of K that is particularly stable and ordered, but still allows the network to change dynamically. And Kauffman discovered that this was at the root of how life on Earth came to be, how proteins assemble and form genes and things like that. And so my work led me to then describing the process of software engineering. Any software engineering process or methodology can be described as a random simulation of the environment, followed by an NKP analysis, because what software engineers spend their days doing is deciding how many components should there be in this system, how should they interface with each other, how should they be connected, how many should be connected to each other. And bias is something that we introduce in software components by using things like contract and schema and validation, and forcing software to behave in a certain way, constraining it essentially. And so every contemporary software engineering methodology can be viewed as a combination of these 2 steps. And this is a great model because it allows us to compare things that are very, very different. And the people who are executing on these contemporary models do not understand that do not see that they are doing random simulation. They believe that they're following a structured process, and they don't know that they're doing an NKP analysis. They think that they're mapping patterns. And so out of this came the ideas that I now call residuality theory. And residuality theory essentially makes the random simulation more random, and it makes the NKP analysis explicit. And it says to software engineers, this is what's actually happening. And so when we look at the problem that we described, the problem with X earlier on, what we're actually doing is that we don't need to think about this entire complex bubble and all of its possible states and all of the possible things that could happen. And then there's further research done by people like Russ Marion who show that social systems also have this tendency with much more complex networks than these random Boolean networks to have a number of attractors. And so the software system that we have to build has to have a structure that's amenable to as many of these attractors in what's in the attractor network for the system as possible, rather than building for just one or shrinking this circle. And so what I then did was I invented the concept of a residue, and a residue is what's left over of an architecture whenever it's exposed to one of these X's. When it's exposed to stress, an architecture will collapse. Some parts of it will stop working altogether because we've changed something in the external network. And so the bits that are left over, the bits that are still running, the bits that can still react to stimulus is called the residue. And what we do is we use this concept of residue as a layer to map between the actual software structure and the attractors that we discover in the network. And so an architecture then, rather than being a collection of components and component structures, is a collection of residues. And so it's an entirely different way to describe them. And so what we end up with is we go into a project and we create something which we call a naive architecture, which comes from traditional software engineering methods. And this is a collection of components or a platform or a particular product which is intended to solve the particular problem. And what we do is we identify X's, things that are going to stress the system that cause the external system to be pushed from one attractor to another. And when we do that and we push it to another attractor, we look at our naive architecture, we say, how much of it is left? Is it still working? Will it still function in this new space, in this new reality? And if not, then we augment it a little bit. We add new components, maybe we add redundancy, we change the component structure. And what we end up with, as we do this over and over and over again, is a number of residues that describe the system operating in different states, different attractors within the attractor network. And what we end up with through this work then is a collection of software architectures. And what we're doing then is actually leveraging something mathematically, and then that is that every residue has a tendency to map to more than one attractor. And that makes sense. If you think about the number of nodes in a software solution, is very small compared to the number of nodes in the social network that surrounds the software. And there's a good body of work from Kauffman and Parisi and Suneson that shows that as n increases, the number of attractors in a network increases quite a lot. And therefore, one residue will map to many different attractors. And every attractor in its turn will map to a number of different stressors. There's a number of different things that can happen in a social system that will push the system to that particular state, which means that for all of these attractors and all of these possible X's, I only need to identify one X to identify the residue that will make my application comfortably continue to function. And that is something that landed well with all of these architects who I talked to, who were able to actually define and build software structures for enterprise solutions and successfully do it. So the job is actually much less impossible than it sounds to identify what is the right architecture, what is the right structure to solve this particular problem, even when many aspects of the problem are unknowable or exist in an unknowable future. And the problem was that a lot of architects can't really work with uncertainty, and this is quite a normal problem whenever we're working with random simulation in human beings. There's something called the curse of high dimensionality. And whenever we try to take random samples, we tend to cluster our sampling around things that we believe have a high probability. And that leads to almost all of our requirements engineering and risk management efforts to be merely a reflection of bias, and usually the bias of the most powerful people who are in the room at the time that we have these conversations, which is why we consistently miss these exits and consistently get this wrong. So there is a mathematical argument for why randomly stressing a system works. The problem is we're not very good at randomly stressing systems because we're subject to these kind of biases. And so I developed over the years a number of techniques to make this more random. And so one of the techniques was to ask software engineers to start off by stressing their system by saying that giant fire-breathing lizards come out of the sea and destroy the city that you do business in, which is, obviously ridiculous. It's not in any business's 5-year plan. I'm sure Elon Musk probably has it, but what this does is it teaches the students that probability is just not part of this. We are not here to judge the possibility or the probability that something's actually going to happen in this network. We want to see what are the structures, what structures would survive these lizards. And if we succeed in doing that, then we have a structure that will survive lizards, but it will also survive flooding, it will survive war, it will survive social unrest, it will survive widespread fire, it will survive infrastructure breakdown, it will survive riots, and it will survive pandemics. And that's an example of this fanning out. Okay, we've identified one X, and that X is the lizards. It doesn't matter whether they exist or not. It matters that we explore more attractors in the wider social network, and that we build our system to cope with those attractors. And very, very often in software engineering, when you do this early, the cost of making these decisions is very, very small. Whereas if there's a pandemic and you'd never modeled any of these things, the cost of making those changes can be exponentially high compared to doing that. And so what we end up with is this residual architecture, which is one naive architecture, which we started out with, and a whole bunch of different residues that describe the architecture in different attractor spaces. And we call the first part of that a stressor analysis. And it takes a little bit of time to teach that to software engineers, to break them out of this this belief that they can predict and control. And we're all programmers are mathematicians of a sort. And so determinism and positivism are something that has to be trained out of them to work with these social systems. The second step then is called contagion analysis. And contagion analysis we'll look at in a minute, but first I'll give you an example of how this works in real life. And this is a stressor analysis from a project that I actually worked in, where we were building a network of fast chargers for electric cars. And we were building the software at the center of this network that would control the fast chargers. And the way this was meant to work, the naive architecture was that I, as a driver, would drive up to a charger and I'd have a little key fob, which I would hold up to the charger. It would identify me, send a message to a back-end server, which would say, yes, he's paid his subscription, which would send a message back. And this would allow me to charge the car. And so what we do then is we sit down and we start to stress the system. We start to come up with as many ways that we can break the system as possible in this wider bubble, not inside the software itself. And so if we look at number 3, which is a failed login, this was a huge problem for the company. These little key fobs, they break all the time. And when that goes wrong, you've got a half ton of metal parked in front of your charger, and there's nothing you can do about it. And that person can't drive anywhere, probably, because their battery's almost flat and they're too far from the next charging station. So how do we solve that problem? We looked at our residue, and our residue was not very good at all. So we changed it, and we added something called ALPR, automatic license plate recognition, so that when you drove up, it scanned your number plate and it allowed you to charge, and then it would send you an invoice later on, even if you weren't registered. And this solved a whole bunch of problems. And so what we've done then is we've changed the structure of our system. And then we take another one here, number 8, which is damage to our chargers, which is something that happens a lot because people drive into them. And there's also a problem in some areas with vandalism. And we solve that with redundancy. Let's have more of these things, and with security cameras, because these things will discourage people to damage the chargers. And another stressor another X that we come up with is something that actually happens quite a lot, is that people drive up to these chargers, they plug in the car, and then they go and play golf. And then and once you do that, only the owner of the car can unlock an electric car from its charger. And that means that our asset is being used for 8 hours, and it only takes 25 minutes roughly to get a car up to 80%. And they're only meant to use them for 25 minutes. This destroys our business model, leads to queues, causes huge problems. And so the way we solve this is to invoice per minute on a sliding scale. So after 25 minutes, this starts to get really expensive. And if you leave the car plugged in for 8 hours, then it's exceptionally expensive. So these are all standard things that most people would do when faced with these problems. But by bringing up these stressors, what we start to see, and this happens in every single project, is that we start to solve problems, X's, that the system wasn't designed for. And here we have a problem down here, a problem called icing. Icing is something that started to happen in the United States, where it was assumed that owning an electric car meant that you had a certain set of political beliefs. And people wanted to irritate people who had that certain set of political beliefs. So what they were doing was they were parking ICE, which stands for internal combustion engine, parking ICE vehicles in front of electric chargers to make sure that the people who owned electric cars couldn't charge their cars and couldn't travel. And this started to happen all over the United States. If you look at the combination of residues from 12, 3, and 8, firstly, we have your license plate. Secondly, we have you on security camera. And thirdly, if you park your car there, we're going to charge you an incredible amount of money if you're there for longer than 25 minutes. That meant that this particular problem wasn't a problem for this design. So we succeeded in solving an X that we had no idea was there. And this pattern is something that, when you use this methodology, is something that we see over and over and over again. We start to build software architectures that solve problems that nobody could see. And if you thought this was a uniquely American problem, it started to happen in Germany as well, where they connected the idea of electric cars to vegetarianism. So they started to shove minced meat into chargers. And no enterprise risk manager anywhere has on their risk register, someone's going to come along and stuff meat in a device. It's just not one of those risks that comes up. But we still built a system that's able to cope with that. And so what residuality theory says then is that a system isn't made up of processes and components, and we shouldn't think in those ways. A system is made up of a set of residues. And those residues are a way of mapping an attractor network to a simpler network, which is a software system. And generally, a residue will have people, software components, software functions, infrastructure, and flows of information between these three things at a very basic level. That's what a residue contains. And once we have those residues, then we have to push them all together to create an actual software architecture. And the way we do that is to use contagion analysis. And so one of the things that we need to think about then is something called hyperliminality, which I'll introduce now. And so this starts with the idea that some systems are ordered, and software systems are very much ordered systems, low K, high P, low N. We're in complete control of them. Social systems, business systems, the society and the market that we have to operate in are disordered systems. Okay, they've got huge N. K is uncontrollable, we can't predict it. And for that reason, I call software engineering the art of engineering hyperliminal systems. And that is that we have this ordered, structured software in this disordered system, and an architect, a designer of these systems, has to live in between these two worlds. One world is ordered and structured, and that's what they teach you when you go to university and learn about software and computing. That's where we spend our time. And then one world is disordered and disorganized and unpredictable. And so to engineer software properly in an enterprise context, you have to move between these two worlds all the time. And there's a guy called David Parnas, and in the early 1970s, he wrote about how we break down software systems into different components. And he noticed that we had a tendency that if I take a business process that has 4 steps, A, B, C, D, and they're dependent on each other, that your average software engineer will give you 4 software components, which mirror that perfectly, A, B, C, D. And they'll do the same for all of the processes in your organization. And what we then do is we group our components based on how functionally similar they are. So if A and D do something which is functionally similar, we group them into one component to try and be effective. And when stress hits this system, if it hits step E in our process, it will hit this component, it will spread to B, it will spread to A and D, spread to C and F, and it will ripple through the entire system, which means the cost of change in that software system is incredibly high. This was a problem when he wrote this paper in 1971. It's still a problem in software engineering today. It's still the default reflex in software engineers. Parnas' suggestion was that what we need to do is design systems for how they're going to change, which is a brilliant idea, much less vulnerable to these ripples. The problem is that he assumed, as a positivist, as a computer scientist, that we knew what was going to change, and we could predict that and design our software from there. So this is the standard way of designing software today. And so Parnas' paper in '72 actually influenced the software engineering industry massively. And so we separate our components from each other based on how we believe things are going to change. What happens then is that we get a stressor that pops up in the system all of a sudden. And from a network perspective, if you have 3 components, A, B, and C, and A is related to B and B is related to C, then that implies there's a relationship between B and C. And exactly the same there. This implies that there is some kind of relationship between component D .
Barry?
Yeah, I'm back. I got kicked out there.
Okay, we lost you.
Yeah, I'm back. So
Nice.
I'm not sure where you lost me, but what I was saying is that whenever stress hits component G and component C, it implies that there's a relationship between these 2 components. And when we look at this at a deeper level, what we find is that there are connections all across these software architectures. And this is why software architecture is hard. This is why projects tend to cost a lot more than they do. This spider web of invisible coupling is what causes software to start to break down. It what causes expensive projects. It means that surprises that pop up in the wider environment cost us a great deal of money. It also maps to a very, very difficult problem within software engineering, which is called non-functional requirements. Non-functional requirements are things like how fast should the system be, how should it scale, what kind of level of availability should it have, what level of security should the system have. And that's very, very difficult for anyone in the business environment to describe to technical people, and technical people have a hard time knowing what level of these non-functional requirements are actually relevant to the software system or the wider business system. And so what we do is we use something called Contagion Analysis, which goes back to the idea of Kauffman Networks and NKP Analysis, to do this in a structured way. And we start by using something called Adjacency Matrices, which comes from, this is how they teach component design at MIT. This is how Boeing and NASA decide which components get to live in the same casing inside a spaceship or an airplane. And what we do is we just put a 1 where there's a dependency and a 0 where there's no dependency. And it's very, very simple. We just look for simple patterns. And what we'll see is these triangles that pop up hopefully, that show a unidirectional relationships that show when you see this triangle, we have a solid process here and we can build software in a normal way. And then what this does is it raises flags for us when we see anything across, when we see mirroring across this line in the middle of the adjacency matrix, then we can say that this is interdependency. So this is either a component that's trying to do too much, or it's a feedback loop, or it's a misunderstanding of how the environment actually works. And this can be worse in certain environments. And if you see these patterns, then these are alarm bells that this is going to be a very difficult system to build. And sometimes we can see that this system is very poorly understood, very immature business environment, or our software engineers have completely lost the plot. One of those things will be true in this case. The last thing that we do then is the idea of an incidence matrix. And what we do is we map stress across different aspects of our residues, such as flow or function or infrastructure. And what we do is we take our list of stressors and we put a 0 if the stressor doesn't hit a component, and we put a 1 if the stressor does hit the component. And what this does is it allows us to make very, very quick decisions about software structure. We can take totals and we can say that this particular stressor here hits an awful lot of components. We need to take care of that. We need to think about that in our structure. And we can see which components in our environment have the highest, most likely to get hit by stress. Those are the ones we need to protect. And those are fairly obvious things. But the really interesting thing is that when we see that a component has hits more than one thing, then that's bringing us back to this ABC or this C and G, and we're saying there's something coupling these two things. And we go back to our adjacency matrices, and if there's no relationship in the adjacency matrix, but there is a relationship here, then we've probably discovered a non-functional dependency, which means we can get to an actual concrete non-functional requirement, which means that if we take care of this now, we're going to save ourselves a lot of pain in the future. Another thing that is really interesting then is that we can go through and we can find the components that have the exact same pattern when exposed to stress. And this could be flows, it could be functions, it could be components. And when they have the exact same pattern when exposed to stress, it means that they can live in the same component. They can live in the same house. And this allows us to make concrete decisions based on something, rather than the way this is done in the software engineering industry today is to use best practices, which obviously don't hold from environment to environment, or by pure guesswork. And so this is more or less what goes on in the head of senior software architects whenever they're able to make these seemingly magical decisions. What then my research is building on is by bringing in a bunch of different architects and asking them, show me your naive architecture. And then I asked them to produce a list of stressors after teaching them how to make this random. And then I asked them from that list of stressors, produce a number of residual architectures and use contagion analysis to reduce that down to one structure. And what we do is we take half of our list of stressors and we hide them. So they have nothing to do with the residual architecture. So we're playing on the testing set, training set idea from ML techniques. And then we run our red stressors, our hidden stressors, which are unknown unknowns for both systems. We run that over N and we run it over R, and we record the number of red stressors that each system can survive. And it's something called a binomial sign test. Then we can show whether or not this kind of intervention actually makes a difference. And from experience, it makes a difference almost all the time. And that entire process is called residual analysis, which means that if you follow this process, this is an alternative to traditional architectural work. So the older architectural frameworks that we've been using for a long time are no longer necessary. And it's essentially a new theory of software engineering. And so you asked me to talk about difficulties in doing this kind of research. So the things that I find really, really difficult doing this PhD, firstly, is the breadth of what I'm doing, because it made me realize how ignorant I was about the world. So my first degree is in pure mathematics. And then my postgrad work is in software engineering and computer science. So the PhD was the first time I'd ever met the concept of ontology or epistemology, because those were assumed in my previous education. So we're positivists here. We don't need to discuss this nonsense. So that was a shock, and it led to a lot of reading, a lot of confusion. The huge scope of complexity science is also difficult. So do we go deep on the mathematics of networks, or do we lean into the more philosophical side of things? And there's a lot of noise from management science, a lot of books, a lot of ideas, a lot of very opinionated people out there, a lot of unverified processes, which are scientifically quite weak in a lot of cases, but they have a lot of influence. So fighting your way through that, understanding what's actually relevant, what was difficult. Another problem I've had is the depth to which software engineers are deterministic in their thinking. There's a lot of people who believe that these social systems can be easily predicted. We just don't know how yet, and we just have to keep working on that. And then I think that the biggest challenge is the fact that software engineering is idiographic. So designing an experiment that worked around idiographic projects. So by idiographic, I mean that it's really difficult to compare two software engineering projects and say that an intervention has worked for both of them, because they're so different. And if you change one thing, so if you have a team delivering a project in a particular market, and you change one thing within that team, within that market, within the software structure, then it's an entirely different thing. And it's very, very difficult to compare. And so doing empirical research in software is a huge challenge. And most of the time it's a fudge. And so actually gathering proper empirical data from software engineers is tough. So it took time to come up with an experimental design that wasn't making dangerous assumptions about things being the same. And possibly the biggest challenge of all is getting people to execute on the experiment, because I have to get a room full of software engineers to understand everything that I've just thrown at you in the last 40 minutes and make sure they understand it properly. And because of the determinism, because it sits so deep in them, there will be at least a few who push back and don't want to be part of it, because the system because they're so programmed to believe that there's a way to predict this, that our methods already work. And there's a natural reaction when you say to people that the way you've been taught to do things, or the way that we've been doing things for 30 years maybe isn't the best way, they'll naturally push back, and they don't want to understand or to do something different. So those are the challenges that I've had. And then initially just finding a supervisor was difficult as well, because I needed someone who could do the math, and someone who understood complexity, and someone who'd seen some software engineering. And so I was lucky enough to eventually find someone who had the breadth to carry those conversations. But it took a year and a half for me to actually find a place to do my PhD. And some schools wanted me to focus on the mathematics. Some schools wanted me to focus on the softer part, and a lot of schools didn't know what I was really describing. And so that's my research project. So I'll open it up to any questions or thoughts.
Thanks, Barry. That was very, very interesting. So do we have any question from the audience?
Well, I have a question. I understand this at the qualitative level, but I don't see the quantitative. How can you do this quantitatively? You know what I mean?
So, yeah. Quantitatively, this is the only way that I've found to be able to do it, to show that because this is an intervention, and so we don't know what is the intervention. It's really hard to quantify how much have I changed this software engineer's mind? How much were they able to do before they turned up in the room? And how much do they understand the environment that they're actually working in? There are so many variables that it's really, really difficult. And so what I'm doing here from a quantitative perspective is called a binomial sign test. And this is the same methodology really that they use when they're assessing interventions within psychiatry or counseling. Because there they have exactly the same problem. We have individuals who are very, very different. We have problems that are not necessarily the same, but we have an intervention that will be more or less the same in every case. And so that's how I'm bringing this to a quantitative conclusion. But I think I'll probably end up concluding that this appears to work in a huge number of cases. It appears to be statistically significant, but you can still, if you can't just believe in this and use it every single time, you could still get burned. Software engineering isn't ever going to be something that follows a very direct formula in that way.
Okay, thanks.
So are there any other questions?
I have one. Can you hear me?
Go on, Lisa.
No, just like I wonder, I don't know if you do actually that, but how do you choose the stressor?
Yeah, so one of the things that we have to do is to teach people how to choose stressors, because if we don't do that, then they end up in this curse of high dimensionality where they just choose things that are familiar to them. So and this is one of the hardest things to teach, is how to break that down and make that really random. So there's a bunch of different tools that I use, which I've pulled mostly from management science, that allow us to explore the business environment in a better way. And we look at things, simple tools like business model canvas. And a business model canvas allows you to describe how a business is built up in terms of its assets and its partners and its customers and its income streams and its costs. And when you understand a business at that level, then you can go through every one of those categories and start saying, well, what if this disappears? What if this breaks? What if this gets replaced? What if something changes that affects our ability to use this? And for a lot of time, what we're doing is we're taking software engineers who've been taught to think like mathematicians, very rigid, very process-oriented, algorithmic thinking, and we're teaching them to be creative and say stupid things. And so getting them to suggest nonsense like lizards is a big part of breaking that barrier down, getting them to come up with it. But generally, what I find is if I teach a class on this, on the first day, people are very nervous. They're very, very difficult for them to come up with a set of stressors. And after a day or two where they start to relax and see how it works, it becomes much easier to come up with these lists of stressors. One of the things that, and this is, I didn't do this empirically, but it's a really, really interesting observation. When I first started teaching this, people really struggled to come up with lists of stressors. And about halfway through, and I've taught about 20 different groups of architects these techniques, halfway through, I took an extra half hour and spent half an hour saying, it's okay to be wrong. It's okay to talk about the stressors. It's okay for your stressor list to be incomplete. It's okay for it to be nonsense. It's okay if you don't think about it right. And immediately after spending that half hour, their ability to produce stress for the systems went through the roof. So a lot of it is about encouraging them to use what they already know, but just to be free with it, rather than having to constantly present this idea that they're thinking rationally, and allowing people to be a little bit more creative. It's not encouraged for some reason, but it's something that comes with practice. And it goes back to the book I mentioned with Sean and reflective practice. People who've been doing architecture for a long time have a much easier time of thinking about stress.
That's amazing. Thank you.
I was wondering, on this exact slide, when you subject one of these residue subsystems to stressors, is this just a prototype of a software system, or is this fully fleshed out and perhaps even in production already?
No, we do this at design time. where it doesn't cost anything. So this is very much a thought experiment. If there are questions that come up during this that we can't answer because we don't know, then that actually informs how we're going to design our prototype. If we can't say that putting this amount of load or this amount of change on a system will hurt it in this way, but if we're not sure about that, then that's a flag. We have to do a prototype here. You can't go to the build phase if you can't answer those questions. It's bad engineering.
I was also thinking that it's very fascinating as a theory, this one of the residuality, and you use it like for this software engineering problem and applications. But I was also wondering, what if we think about maybe other different systems in which we can use this kind of theory? For example, I was thinking about human brain, how we process all the information around us, and maybe could be that we also have some residuals in our neural processes, if you want, because we are subjected to the environment as well as the software you studied, and maybe there has to be could be a way to express some of the neural process, human neural process, in the processing of all the information we have from the environment. Do you have a think about it, or do you know if?
I can't help myself from what, you know, when I work with this in software, I'll go and I'll look at a different problem and I'll think about how do our brains work, or how does an organization work, and I'll look at, hey, actually you could apply this kind of thinking to that idea. But I have a lot of people within the management science sort of complexity community are interested in how these ideas apply to organizational design. And what I've said is that it's interesting, but it needs to be researched properly, because you can't just apply the ideas directly from software to human organizations. They're not hyperliminal in the same way, in that a human organization or a brain isn't as straightforward, isn't as structured, and isn't as controlled by us as a software system. So a lot of my assumptions and a lot of that mathematical leverage might actually disappear in systems that have a higher number of nodes or a higher K in the middle. So software's properties, the fact that we control it, makes it easier to reason in this kind of way. We might miss things, and so there are some other researchers in the Netherlands who are looking at how this might work for organizational design, which is interesting. But I don't have time to try and to do that as well on top of
I understand, but it's really fascinating because it could be applied for other systems.
Yeah, it's essentially at the root, residuality theory is epistemological. It's saying that the only thing we can know is that things we don't know about are going to happen, and that when they happen, they're going to damage our system in some particular way. And we don't know what's going to be left, and we don't know what's going to be running. And it's just a way of viewing systems as a system, as just a collection of broken systems across a range of probabilities that we don't understand. So it's really, as I said in one of the slides, it's just another layer of abstraction for us, which is what computer scientists do. Right? That's how we navigate reality.
I also found that the problem of the rationality against the random world, it's really interesting, and I found interesting that you cannot found someone that easily say, okay, I'm wrong with it. I have to find something wrong to prove the strongness, the robustness of the software. So that it's like the war between rationality and chaos, and
yeah, it's difficult conversations sometimes too.
Yeah, also because they are okay, if you want, biased by their own career, working on softwares that, as you say, they are very controlled systems, and there is no place for chaos in a program, if you want.
Yeah, that's it. It makes it difficult. Yeah.
So.
Okay.
Any other questions or ideas that come up from the audience? All right, so maybe we can stop here. And thank you very much, Barry, for your presentation. That was very interesting. And yeah, let's see you, I hope, in the next NetPlace. And see you later, guys. Have a nice day and afternoon.
Thank you, everyone, for listening. And I'll see you next time at this meeting.
Yes.
Yep.
Thank you, guys.
Thank you.
Bye.